We're in the home stretch for stoichiometry now, and we're having to pull weird cases out of our hats, like things that have more than 2 reactants. And this takes a little bit different approach, and we've done enough stoichiometry now that you may be able to just look at stuff and come up with answers to some degree, and we'll utilize that skill later, if you want to. You don't have to, because we can treat it like a single elimination tournament in weeding out which of these things is limiting and excess, and find the winner, the limiting reactant. In fact, let's make a note to ourselves in advance here. If you have 3 reactants, you're going to have 1 limiting reactant, and you're going to have 2 excess reactants. And the key is, and I want you to remember this for later, those those excess reactants, the amounts are relative to the limiting reactant. So the amounts must be relative to the limiting reactant. And so the first time we do this problem, I'm going to make sure it's as miserable as possible for us, and I'll explain why. So here's how this is going to work. I'm going to do it as a single elimination tournament, and we're going to do it in the most brutal, painful way possible. And then I'm going to show you how it could have gone a little faster, and then I'm going to show you the fastest it could have gone. And that doesn't mean it's a quick problem, but take note, we're deliberately making it as annoying as we could this first time through. We're given some amounts, and let's just get those written down very quickly here. 20 grams of ammonia. And I'm going to step on sig figs quite a bit here because I just want to get the problem done. 60 grams of oxygen and 40 grams of methane gas. Our molar masses I already gave up top. Divide by 17.04, 32, and 16.05 grams per mole. Right? Ammonia, methane gas, that's natural gas. Just to give you some relevance on those, this is going to end up 1.17 moles of ammonia. This will be 1.875 moles of oxygen and 2.49 moles of methane gas. All right, this is our bracket as I set this up. These are the things that we have, right? As we look at the terminology that I've used in previous videos. And this is what we're going to use for our bracket. Do take note. Slight omission there. All right. And if you've looked at brackets before, it starts out something like that. And then there's a first round where some teams compete. Well, in a real, say, basketball scenario as it is March, you don't have 3 teams on the court at once. You're just going to have 2 go on. And I'm going to plan ahead. Because I know the answer, I'm going to make these 2 compete in the first round because that's going to make more work for later. And whoever the winner is will compete against ammonia in the next round of the bracket to see who the overall limiting reactant is. All right? So ammonia automatically makes it to the next round of this bracket. Oxygen or CH4 will make it. And whoever is knocked out along the way, excess reactant, and then this will be our limiting reactant in the end. All right, so let's start by comparing these 2 things, the oxygen and the CH4, and let's get it going. 1.875 moles of oxygen and 2.49 moles CH4, and that's what we have. We need to compare our reactants to each other to find the limiting and excess. We're going to use the balanced chemical equation for everything after the first box here. Oxygen, 3 of those. And CH4, we've got 2 of those. This is going to tell us what we need of each of those things so we can find out who wins the first round. We have 1.25 moles of CH4 that we need, and 2.49 times 3 divided by 2 ends up 3.74 moles of oxygen that we need. A quick comparison here, we have 1.875 and we need 3. We don't have enough oxygen, so that becomes our limiting reactant, and CH4 is an excess reactant. I'm not going to circle it here because that's a very dangerous thing, but oxygen moves on to the next round. So what are we going to do in the next round? Well, we're going to compare ammonia and oxygen this time. We'll go back to what we have of those things. The ammonia, we have 1.17 moles, and the oxygen, we have 1.875 moles. And now we do our comparison. For the ammonia, I have 2 moles of ammonia for every 3 moles of oxygen. We find out that we need 1.875 times 2 divided by 3, 1.25 moles of NH3, and 1.17 times 3 divided by 2 is 1.76 moles of oxygen. As we look here, 1.17 is what we have, 1.25 is what we need, 1.875 is what we have, and 1.76 is what we need. I don't know if I said those words correctly, but have 1.1, need 1.2. We don't have enough ammonia. So that is our limiting reactant, and oxygen becomes excess. Ammonia is the limiting reactant for this process. And something that I think isn't super intuitive, but you can kind of brute force it, is if oxygen is limiting compared to methane, and ammonia is limiting compared to oxygen, then ammonia is definitely limiting compared to CH4. And another way to think about that in like sports terms is, if oxygen can beat CH4 and ammonia can beat oxygen, then theoretically ammonia could have beaten CH4. Now here's where we run into a problem. Our amounts for our amount excess have to be determined relative to the limiting reactant. Well, since CH4 never was compared or never played against NH3, I don't have the number I need. So I need to add in one more comparison right here to get our amount. So I put that in that color. Let's see if we can duplicate that in some way. I need to compare the ammonia to the CH4. And I intentionally set it up to be annoying like this because it makes it a little clearer and less painful when we can see the faster ways to do it later. Alright, perhaps you've heard the word have before, and need. The good news is we only have one comparison to do, and that's going to be comparing the NH3 to the CH4. So we have 1.17 moles of ammonia. We know that for every 2 moles of ammonia, there's 2 moles of CH4. So we should end up with 1.17 moles of CH4 that we need. And now we have the tools at hand to come up with our amount excess. And we have 2 excess reactants, the 2 losers in the bracket. I don't know, the loser, well, so these guys ended up being excess reactants. And so we're going to get our amount excess the same way as always. We're going to take what we have and we're going to subtract what we need of those things. So the first thing we have 2.49, oh, I can't use that one. We have 1.875 moles of oxygen, and I need 1.76 moles of oxygen. So 1.875 moles of oxygen, and I need 1.76 moles of oxygen. All right, and then for our CH4, I have 2.49 moles of CH4, and I need 1.17 moles of CH4. Okay, and the numbers that I chose to do that might be worth identifying. I had 1.875, and I needed 1.76 for the oxygen. I have 2.49 for the methane, and I needed 1.17 for the methane, and that's where these came from. And again, it's because those things had to be compared to our ammonia. Ammonia wasn't up here, so I couldn't use that number. So here is ammonia, and that's why that comparison matters. Here is ammonia, and that's why that number matters. And in fact, instead of saying 2.49, I could have gone with that, 2.49. Now that that's sufficiently muddier, let's get our amount excess in grams and move on with our lives. We'll multiply by our molar masses. Sorry, actually, we'll get our subtracted numbers and then multiply by our molar masses. This is 0.115 moles of oxygen, and this is 1.32 moles of CH4. If we multiply by their molar masses, which are 32 grams per mole and 16.05 grams per mole, we get our mass amounts, and those numbers are 3.68 grams of O2 excess and 21.2 grams of CH4 excess. And that is something we could be looking for in this problem. We found an amount excess. We found our limiting reactant and we found our excess reactant. And now we want to use our limiting reactant to find out about our products. And as you may recall, our limiting reactant was the NH3. So the NH3 becomes the number of choice for our future calculations. And we're going to see how space works out here. We want to do the blue step here. We're going to use the limiting reactant to find out our theoretical yield. We've got 1.17 moles of NH3. And now we've got two products, so I'm going to set my dimensional analysis up with hopefully room for two products there. We know from our balanced chemical equation 2 moles of NH3. We're looking at 2 moles of HCN and 6 moles of H2O. And let's get the caps on these. This gives us 1.17 moles of HCN. We can multiply by our molar mass, which is 27.03, and we get 31.7 grams of HCN. That's our theoretical yield for that one. For the 6 moles of H2O, this gives us 3.52 moles. And when we multiply that by the molar mass of 18.02 grams per mole, we end up with 63.5 grams of H2O. And those numbers there are a theoretical yield. Let me get my markers sorted out very briefly. Let's put a box around that maybe. That is something we were looking for in blue on here, so let's just say it's blue on there. That's our theoretical yield. And this is our amount excess of the other two. And then we can get a percent yield, and I don't know why I bothered putting that into this problem because it's big enough as is. But I had said that 57 grams of water were collected in the lab. We know how to calculate a percent yield, and I made some bad color choices earlier, so we're going to have to switch to this. Our percent yield is supposed to be the actual over the theoretical times 100. And in this case, that is 57 grams that was given over 63.5 grams times 100, and that is 89.8% yield. And I guess that is an answer as well. All right, at that point we could find the actual yield of the other reactants and stuff like that, but we've addressed all the key points of this problem. And it seemed like a bunch of work. Like we did 1, 2, 3, 4, 5 different comparisons just to find our limiting and our amounts excess. So let's do some planning this time and see if we can cut some corners. All right? What went wrong here was I had to do an extra step at the end where I compared the NH3 to the CH4 because NH3 wasn't in the first round. So initially what we could do maybe to streamline things and limit ourselves to 4 comparisons would be to say, let's look at our ratio in advance. I need more oxygen than CH4 or ammonia. All right? There's 2 of those, 3 of those, 2 of those. So in fact, I need equal molar amounts of NH3 and CH4, and I need 50% more oxygen in terms of moles. So what I can look at my mole amounts down here, what I have, I'm going to look and see if oxygen is the biggest, if oxygen is what I have the most of. And as I look here, oxygen is not what I have the most of. So in my head right there, it's like, okay, oxygen is an immediate winner potentially. But then I have to say, do I have like 50% more oxygen than ammonia? And so if we look at our ammonia, that's 1.17, and half of that's like a 0.6-ish, and so that'd be 1.77. I don't have enough ammonia, or actually, sorry, I have excess oxygen there, all right? And then if I look, do I have 50% more CH4, or sorry, oxygen than CH4? And as I look here, I've got more CH4, so that has to be excess, and I've got way more CH4 than the NH3. I don't know. It's with a 2 to 3 ratio, it's a little harder, but it's 50% more. So what I would say in the big picture, and as we look at the next problem, is best case scenario would be to start out your tournament with NH3. And I'm not even going to do it too detailed, but let's just pretend. So let's say slightly more efficient. Seed better. Seed the brackets better. And what I mean by that is we're going to predict our limiting reactant by looking at those ratios there, and then we're going to make sure it's compared to both. It doesn't have a buy in the first round. It compares to both. All right? So let's look at what that tournament would have looked like and look at how it would have gone at least a little faster in this case. So let's redo our bracket. I'm looking for my pen here. There we go. We've got our 1.17 moles of NH3 and 1.875 moles of oxygen and 2.49 moles of CH4. And from the previous problem, or from our horrible mental math earlier, we know ammonia is going to be the limiting reactant. So I want to make sure ammonia seeds into the most games in the bracket. So I'm just going to declare that as we set up our bracket, ammonia is going to be the limiting reactant. We're going to make sure it has to play the first round. And what's going to happen then is in the next round, when ammonia is going to win, because it'll still be limiting, and we'll double check that, I'm going to compare ammonia and methane, and ammonia is going to win overall again. It'll be our limiting reactant. Same numbers, same process, but it cuts out this step right here, where we needed to compare our limiting reactant to that. So I will try and sketch that out super quickly. So we'll start with the NH3 and the O2 this time. And it doesn't matter. You can pick any ones you want. But we'll try setting up our halves. For the NH3, we have 1.17 moles. And for the O2, we have 1.875 moles, right? I'll do this not in black. This is what we did. I'm just sketching things out here. We know that for every 2 moles of NH3, I was supposed to have 3 moles of oxygen. And we actually did this comparison right here, and we knew it was 1.76 moles of oxygen and 1.25 moles of ammonia. And knowing what we know, 1.76 is less than we need, and 1.25 is more than we have, and this becomes the limiting reactant in the first round there. So then in the next round, we're going to take the NH3 versus the CH4, and we'll do a double comparison like we did. And then once we get down here to a separate plan, I'll show you how we could have cut even that step out. So we'll take our 1.17 moles of NH3, and this time we're going to look at our 2.49 moles of CH4. Now, I did separate over here, so I will separate these steps over here in the same way. That's what I have, and that's what I need. All right, now we'll cut up and labeling things. I want to point out that this is the red marker, and this is the orange marker, and they look almost identical on the page. Quality products. CH4, 2 moles of CH4, 2 moles of CH4, and then our NH3 is 2 moles of NH3, 2 moles of NH3. All right? So 1.17 moles of CH4 is what we would need. I have way more than that. And 2.49 moles of NH3 is what I would need. And I certainly don't have that. So once again, ammonia takes that round, and it becomes the limiting reactant overall. And then we have to do this step again still. All right, so we can't escape this right here. That's going to have to happen no matter what. So that was a bit faster. We only did 4 comparisons to find our limiting and excess, and we had the information we needed to get our amounts excess relative to the ammonia. So like, this is what I want to make sure my colors match. This is what we needed of the CH4, and this is what we had of the CH4. This is what we needed of the oxygen, this is what we had of the oxygen, and those are the numbers we used down there. All right, so that's faster. It can be done even faster if you want to plan a little bit better. You know that the limiting reactant is all that matters, and comparing to the limiting reactant is all that matters. So you can super cheap shot this whole thing if you have some planning, right? I guess a faster way to look at this than I did before, we should have the same molar amounts of ammonia and CH4, same amounts. As I look, I have way more CH4, so ammonia would be the limiting reactant there, right? So I've compared those two things in my head and said, oh, NH3 is going to win in terms of being a limiting reactant because I'm supposed to have the same amount, and that number's bigger. So now I'm going to look at ammonia versus oxygen, which I did before, and you got to say, well, that about half of that is 0.6. 1.17 plus 0.6 is 1.77. That's not enough ammonia to use up all that oxygen. So ammonia is going to be my limiting reactant. So if you just plan ahead and declare this is going to be my limiting reactant, and you got to plan carefully, then you can take care of all of this, well, except for this, and all of this in one set of brackets. And let's see how that would look. You'd take 1.17 moles of NH3. I'm already very unimpressed with my space budgeting. Everything after the first box comes from the balanced chemical equation. We know that we've got 2 moles of NH3, right? The other things that I want to know about, if NH3 is the limiting reactant, if I only needed to know about products, I could just do this and be done. So realistically, if I didn't need to know the amount excess, I wouldn't have to do any of that. I'd still need moles, and I could do that and be done. But we're going to say that we want to know these amount excesses to check, or whatever reason that we have. We're going to compare everything, okay, and I'll put them all in one box. For the oxygen, I've got 3 moles of oxygen. So that's going to tell me what I need relative to the oxygen. And we already know that number. It is 1.76 moles of oxygen. And that's a need, right? We've got our CH4, and our balanced chemical equation tells us 2 moles of CH4. And we will end up then, we've seen this before as well, 1.17 moles of CH4. All right, those are the reactants that I wanted to know, and now let's talk about the products that I wanted to know. We have HCN, so there's 2 moles of HCN, and that is 1.17 moles of HCN. That would be part of my theoretical yield. And then we've got 6 moles of H2O, which would give me 3.52 moles of H2O. And we've done this math before with the masses and everything. These two numbers are our 1.76 and our 1.17. In fact, I guess I can highlight those. We have the information we need there and there relative to that to give us that highlighted stuff there. And then for our theoretical yield, we have this comparison taking place right here. So you can do, well, you can't escape doing the moles. You can escape doing 5 comparisons. You can escape the excess if you're not asked for it. You can't escape this step to get the products. This streamlines things, and this is all that's really happening to get this and this. All right. I'll try and break this up color-wise in terms of like mandatory and not. There was no way to escape this particular step, turning grams into moles. No matter which of these things you did, you couldn't escape that. You had to have a balanced chemical equation. If, assuming we were asking for an amount excess, then this had to take place. And there was no faster way to do this, this, or this. You could then have done this for your comparisons, and then done this to get your theoretical yield and your percent yield. Or you could have streamlined things ever so slightly and done this along with this right here. Or you could have streamlined things even more. I'm looking for a color here. And done the red stuff and this right here. All right? So the fastest it could have gone. This, 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 this. Everything else was slightly longer, but shows a little more of the work, which is not a bad thing. We'll try it again in the next example.